Hello again. My name is Mohammed Lamin, and I am a PhD student at the Department of Measurement of the Faculty of Electrical Engineering of the Czech Technical University in Prague. And also I work as a research assistant in the Laboratory of Rotational Laser Vibrometry in the Institute of Thermomechanics of the Czech Academy of Science. So in this presentation, I would like to show you both like my working place, the laboratory, what we do in the laboratory, and what kind of the problems that we deal with. And also I would like to share some of the results or the problem that we try to resolve. So the definition of the laboratory is one of the unique laboratories in the world. And actually in Europe, there is only 2 laboratories that are equipped with these materials. So the objective of our lab, the lab of rotational laser vibrometry, is to make activities on vibration diagnostics of rotating machines. And basically we measure the rotating blade vibration in order to diagnostic the structural health of the blades and enable like online monitoring of the blade condition. And the second activity or the second objective that we deal with in our laboratory is the development of non-contact measurement system. Mainly, we try to develop like blade tip timing measurement system based on magnetoresistive sensors. And I will explain later what is this blade tip timing. In our lab, we have like test rig systems that we built on ourselves. We have also a laser Doppler vibrometer system, which can be seen in the picture. And we have also like 2 different other measurement systems, which are like blade tip timing system, which is now under development. And we have also like used the classical strain gauge measurement system. Our lab or our lab test rig include like a rotary model. This rotary model is like connected with an electrical machine that can drive a rotor up to 7,000 RPM. And this rotor can be changed to fit any type of first stage compressor bladed disc, or like even like more developed or like self-designed like rotating disc. The full assembly is located in a vacuum that can be closed to ensure that there is no aerodynamic forces that are applying on the blades. And this is like thanks to the 2 pumps that are connected to the vacuum chamber, which can be seen here. This vacuum chamber can ensure only like a variation of 5 millibar of static pressure inside. Also, our system is equipped by a control unit. This control unit can enable like several maneuvering procedure. We can accelerate with different rates or decelerate with different rate. We can also like have like static speed. We can control even like the speed regulator in order to have like small speed fluctuation. Our rig also is like equipped with the auxiliary excitation system, which is like some electromagnet that are like mounted in the back and in the circumference of the rotating disc in order to amplify the vibrations, so we can better have like bigger amplitudes. And this is more to calibrate or to study the real vibration that are occurring in our system. The magnetic excitation system that I was speaking about is consisting of 16 electromagnets that can be also controlled from control units in order to impose the blades or the rotating machinery to vibrate with specific frequencies and also with specific amplitudes. We have 8 axial and 8 radial. And as I told you, it's offer a lot of excitation type. We can use the DC excitation modes. We can also have like alternative harmonic or pulses at any parameters that we can decide. The LDV is developed by Polytech, and we have like a PSV 500 equipped with the rotator, and we have like reference vibrometers. The possibilities that offered by this system consist of the possibility to measure the vibration during rotation, and thanks to the rotator that is equipped inside, the measurement head is connected to the data management units and that can enable the signal processing operation, which you can do FFT or FFT. You can integrate, you can derivate or filter the signal that you acquire in order to meet your objective. Mainly in our laboratory, we measure two quantities, which are the displacements or the velocity of vibration. The blade dip timing system, which is now under development in order to enable the online monitoring of blade vibrations. And in our laboratory, we have our own system, and it's based on magnetoresistive sensors, which can be seen in the pictures. We also what is BTT is like the sum of sensors that are located on the circumference of the bladed discs, and each sensor work is to record the exact time when the blade crosses under this sensor. From the time data, we can later reconstruct the signal of vibration of the machine. The last system that we have is an auxiliary classic system based on strain gauge, but what is different in this that we don't need to wire the strain gauge to a data acquisition unit, because we have this telemetry board which is developed by EMTD Ltd, and it's like a subsidiary of Rolls-Royce, and it enables the transfer of strain measurement from the bladed disc to the data management unit without wiring. It's like using radio frequencies. One of the projects that we worked on and that this study is based on was Year Horizon 2020. It's Batista project, where we tried to make measurements on a compressor from a Viper 522, which is an aero compressor of a real jet fighter, which was developed also by Rolls-Royce under a project called Olympus. And the aim of this objective was to define the mistuning of the blades. The mistuning is like the blades vibrating with different frequencies. Our objective was to validate the blade tip timing developed by EMTD Ltd. As I said, this is a subsidiary of Rolls-Royce, with our laser Doppler vibrometer. As I explained before, the blade tip timing consists of the distribution of this sensor on the circumference. Of course, the number of and the location of the sensor must be studied and defined before. The sensors will give us time data, and through some mathematical operations, we can translate this time data into displacement per time signal. And through this signal, we can derive the characteristics of the blades. Mainly the equation, or the simplified equation of the vibration, can be written as the sum of sine and cosine functions plus a constant component. The beta ks and beta kc are like Fourier coefficients of the cosine and sine functions. This fk is the natural frequency of the blades. Of course, when the blade is vibrating, it can vibrate with several modes, so it can include one or two, or let's say it depends on the resolution of your measurement system. Okay, the blade tip timing charts consist of course, the objective is to quantify the blade vibration, so we should know the amplitude and the frequency of vibrations. And the most pillar things is to define where to put the probes and how we will arrange these probes in order to get an accurate time of arrival. As much as your time is very accurate, as much as the error is very small. And if the error is very high, and now in the commercialized system is around 20%, and it's very high, all what comes after will be like with a huge error. For example, if you want to estimate the structural health of the blade, you will not be able if the error of recording time is very high. So the positioning methods developed also through time, but they are developing very slowly. And they are classified based on the vibration itself, like they anticipate or they estimate or the type of the vibration signal. They think like these blades will vibrate only with asynchronous vibrations, so we will use directly these methods. So it's kind of standard. Or if it's vibrated with synchronous vibration, we will use these methods. So they have like kind of standard, and they pick the relevant method based on the estimated like type of vibration. Mainly, and the most used is these methods that I resumed there here. And the location of these sensors depend on the geometry of the turbine or the aero compressor. And the only factor that they take into consideration is a factor called the condition number. And the condition number more give you the stability of your function, not the error size of the function. So they put like standard, and they said like if the condition number is less than 10, we will just adopt these methods. So what we do, we just propose new methods based on some statistical factor, and these methods can be determined as follow. We choose the angular time resolution, we choose the setups, like how many sensors we should include and where to include. We choose the true model, we include the geometry restriction, and we choose the simulation setup, how many time series we should include, how much the period, how much the speed. And at the end, we'll estimate the statistical variable, mainly are the bias, the standard deviation, and the root mean square error. And based on this, we choose our best positioning. As you can see in this slide, this is like the formulas of the root mean square error, the standard deviation, and the bias based on the equation 1. And through this, we proposed the scenario. The scenario is like we propose multiple scenarios, but we focus in this presentation on just one. The scenario is assumed that the blade is vibrating with a single frequency, which is 300 hertz, and with a phase of P/4. And we assume that the real amplitude is 141 micrometer. We also suppose that this vibration is corrupted by noise. Mu is the mean of the noise, and the sigma is the standard deviation. We suppose that the standard deviation is around 10% of the minimal amplitude of vibrations, and we suppose that the wheel is turning with 3000 RPM. We summarize the result in these two tables, and in the first case, we didn't make any restriction on the angles between like two consecutive probes. We just say like give us 3 probes, which in each case give us the minimum root mean square error, or like the minimum standard deviation, or the minimum bias. We found that this configuration and this number are untilted to specific location in our turbine circumference, and we found that this is the best configuration. The configuration 358 give the less error in the reconstruction of the signal. In the second case, we reduced the standard deviation of the noise to 0.1 micrometers, to a very small value, and we also integrated we implemented in the algorithm that the angular resolution should be 20 degrees. And we found that the best is also the same configuration that were obtained from the first scenario. The analysis of the results show that these new methods, these new statistical methods that depends on this root mean square error doesn't or have an immunity against the geometrical restriction, because it doesn't take into consideration the angular resolution. So it can work either in regular or irregular distribution, and it works with both synchronous and asynchronous vibration. We had other scenarios and where we included like several or multiple frequencies. We also changed the amplitude, but the results were always the same. This work was mainly theoretical. We are waiting for a new wheel to test our theoretical results experimentally. And we want to prove more the process, as I said, experimentally. We want to include more geometric restrictions to optimize our process. And we want to include a review about the classical methods and this method. As you can see, this is the new wheel, which are now mounted, and we wanted to make the experiments on it. It's developed by Dusan Škoda Power in Czech Republic. It has 60 blades, and we hope that everything will be like, will go according to plan so we can make the experiment as soon as possible. This is the 3D design of the blades that we suggested in our laboratory. As I said before, the difference between our laboratory and the other laboratories that we include the real aerodynamic shape of the blades in our experiments. So mainly other laboratories, they assume that the blades are like just like rectangular, that they has only a rectangular shape. So for us, we test real blades. We made some tests and we found that the error, this was like preliminary test. We could extract through the LDV and through the finite element methods the natural frequencies of the blade, and we found that we had like very small errors. So we are expecting that the error in our new methods will be like less than those. So this is all from me. Thank you so much for your attention.
Thank you for your presentation.